The diffusion and migration rates are due to a large number of ion jumps per unit time in a certain direction compared to other directions. Statistical analysis of this process shows that the diffusion flow, that is the number of particles diffusing through a unit area per unit time, is proportional to the concentration of these particles and the gradient of their chemical potential. A minus sign indicates that particles are moving in the opposite direction to increasing concentration. The proportionality constant can be expressed in terms of the average length of the ion jumps and the activation energy necessary for these jumps. Then the equation can be rewritten as this equation is known as Fick's first law. On the other hand, the migration flow is proportional to the ion concentration and the gradient of the electric potential. The minus sign is due to the fact that the direction of motion of the cations coincides with the direction of the field. And the field? The proportionality constant is called the electrical mobility of the ion. It determines the average ion velocity at a unit electric field strength. In the general case, an ion moves both under the influence of a gradient of chemical potential and under the influence of a gradient of electric potential. Therefore, the total ion flows is the sum of the diffusion and migration flows. And the general force acting on the ion is a gradient of the electrochemical potential determined by the ratio. If ions do not move in solution, then in other words, the distribution of a given kind of ions in a solution that does not change over time can be the result of mutual compensation of chemical and electrochemical potentials. This allows us to establish a relationship between the electric mobility of the ion and the diffusion coefficient. Since Then taking into account the equation, we get, and if we substitute this expression into the equation, so we get let's use the following assumptions. In this case, this is the Nernst-Einstein equation. It relates the diffusion coefficient at infinite dilution with the electric mobility of the ion. From a comparison of the formulas, it is possible to obtain a dependence of the electric mobility of an ion on the average length and activation energy of ion jumps in an electrolyte solution. Let's consider the diffusion of an electrolyte which completely dissociates into ions from the region of a solution of concentrations of C1 to C2. If the diffusion coefficients of cations and anions are the same, then the process is no different from the usual diffusion of uncharged particles. However, if they differ, then specific phenomena occur in the electrolyte solution. Suppose that under this condition, anions at the initial moment of the diffusion process will move from left to right faster than cations. As a result of this, a special separation of charges will occur and an electric field will appear, which will accelerate the movement of cations and slow down the movement of anions. Consequently, after some time, the speed of movement of cations and anions align, and in these conditions, we can speak about the total flow of electrolyte. However, this flow is not an ordinary diffusion flow, since the so-called diffusion potential is established between two regions of the solution with different concentrations. Assume that the Nernst-Einstein equation is valid not only in an infinitely dilute solution, but also at finite ion concentrations. Then, for the general flows of cations and anions, we obtain the ion velocity can be determined by the relation. Since in stationary conditions, then since then solving the equation with respect to the potential gradient, we obtain and the total speed of movement of cations and anions in stationary conditions is determined by the formula. Then the total electrolyte flow can be represented as the term effective reflects the fact that in reality the movement of ions under the consideration conditions occurs not only due to diffusion, but also under the influence of an electric field. The expression for the diffusion potential can be obtained by integrating the equation for the potential gradient. It will have the following form. For the system shown in the figure, the diffusion potential determines the potential difference between the right and left parts of the vessel, separated by a porous septum. Under conditions, diffusion potential will be less than 0. This corresponds to the fact that the right side of the porous septum is negatively charged with respect to the left side due to the initial faster diffusion of the anions. If the diffusion coefficients of cations and anions are equal, the diffusion potential is equal to 0.